Again, in this short discussion, I'm going to talk a little bit about some of the resources we have and prepare you for the project. So, if you go to our website, you'll find that we have this tab called Other Resources. And on this tab, you have a number of videos that I have here, but I also have certain aspects that you should be cognizant with. One of them is this one here, thermochemical properties from the National Institute of Science and Technology. And the other one is a NASA chemical kinetics software. The NASA chemical kinetics software, we may not need it for now, but in the future you could use it when we try to do some CVD problems. But for now, you should go to this web book for NIST. And the web book, it says, Welcome to NIST Chemistry Web Book. And you have Standard Reference Data Program, and then you have this NIST Chemistry web book. So if you click on it, then you will get the profile that looks like this. And in here, if you're looking for specific properties, you can have your properties if you enter a formula or the name of the element or the compound or some identifier that they're familiar with and so forth. So I have not explored all of the possibilities because NIST has tremendous database. But if you just simply click on name, for example, and I would like to know the properties of one of the elements. Suppose that I am interested in copper, for example, Cu, and I want to have the gas phase data, and then I can actually search to see in the database. They have copper, and they have ionic copper plus and minus. So if I'm interested in copper, then it gives me a lot of information on the copper. And the important one is that I have here, as you can see, the gas phase thermochemistry data for copper. We have other data, condensed phase thermochemistry data. So if I click on the, let's say, the condensed phase thermochemistry data, then it gives me the following. So it gives me here the most important aspects. These equations that you see, this is the specific heat as a function of temperature. This is the enthalpy as a function of temperature, and it is evaluated from the STP. And this is the entropy as well. And then you notice that you have these constants A, B, C, D, and E. These are constants because you represent the data in terms of polynomials. And they carry through because you do integrations to get the H, but they have additional constants like the F and a G coming from the integrations. And at the end of the day, you have for this temperature range, then you have 1, 2, 3, 4, 5, 6, 7, 8 numbers or 8 constants. If you know these constants, then you got it made, because you can get the liquid phase heat capacity, all of the properties for the liquid phase, all of the properties for the solid phase. You have the constants here, and you can decide phase equilibrium, and you can use it for mixing and so on. Now, at the transition between the liquid and the solid phase, you have a delta H. This is a transition, and also you have corresponding S0 for solid and S0 for liquid given in the table. So this is kind of an example of how to use the thermodynamics database that we have here for NIST. And I think I have not myself explored it in great detail, but I think many of you would be wise to look at it, because you could use it in your research, or you can also use it to solve specific problems in thermochemistry, and you become a real expert in alloy design, material design in general. So now the next topic that I want to discuss today is how do you prepare your project. What is the project is about? And I thought that the best way really is to show you examples of projects implemented by students in previous years. So I'll bring up a couple of examples on the screen, and then I'll point out what is going on with these projects, and then we discuss what you can do at the present time. So I'll put myself on the side here, and then I'll pull up Nick Papiri's design project for the casting of a connecting rod. So I mentioned in class that I'm going to provide you with a template. So the template is going to be in here, similar to this template, and it will be a file that you have the title in here, design of the casting process. So you are a designer and a manufacturing engineer of an internal combustion engine rod. And then we have the grading here. You got a good grade, 91 at the final, and this is what he had put into the project. So he put in about 30 pages or so. He has an abstract, list of symbols, introduction, and then a review of the casting of steel products, because this is research, literature research. And then he did modeling in simulation conditions. And the modeling that he did, he used a couple of techniques. So one of them is analytical, following what we will do with you in class. And then the other one is a little bit more advanced, using finite elements, so you can practice to become a real design engineer, and discussion of the simulation results and summary and conclusions and acknowledgements, references, etc. So if you look at here, the abstract is you write it basically at the end of the project, and the abstract should not becomes a summary of everything that is inside the report, but it should be something that an individual who is interested to know about your work can read it and get a good idea about the assumptions that you made and the method that you implemented and the conclusions that you have. So conclusion is very important to restate. So you have objectives, methods, and assumptions and conclusions. So these are the four things that you should include in the report. Assumptions, methods, objectives, and conclusions of the work in about 200 words or so. And they have the list of symbols, and the list of symbols, do not forget to put in the units in the project. So when you do the list of symbols, it saves you time, and it saves you time inside the report to say K equals thermal conductivity multiple times. You just state it at the beginning, and then you give it the, as you can see here, you give it the units in watts per meter K, and you're done. So that's the list of symbols. Next is the introduction, and that is important because you can reference a number of references, like you say here, Riddy, 2007. These kind of referencing you should be familiar. If you use Word, then in Word there are possibilities to build a bibliography automatically, and you can put in the references by yourself in Word, and then it will bring it in the correct format, like a Chicago format or some other format that you can choose. So most of the referencing would be in the introduction, reviewing here what's going on in the casting area and what are the problems, what are the drawbacks, what is going on with the connecting rods, and what kind of materials, alloys, and so forth. It's up to you what you actually discuss here, because it's a big field and you choose your own way. And then he wanted to specialize in casting of steel products, and then discussed a little bit about the heat transfer problem and the effects of radiation and so forth. So it's all of a discussion. And then he's trying to say that during the solidification, you get the temperature kind of decreases, and then you get a solid liquid mix. And that's the big problem in casting, is that you get solidus and liquidus lines, and those give you you have to solve for be able to kind of track the front of the cast, or the front that represents the solidus and the front that represents the liquidus in the solution. So there's some method to do that. And then he goes into the real problems in casting, where you have like grain, the solidification starts from the outside of the mold, and then the grain size becomes cooler, and then the grains will change until you get to the core, and what happens to the grain size, and how you can control it, and so forth. And here's an example where you can have quite inhomogeneous material, because the strength of the material depends on how you control the grain size and how you can have it more uniform if you want. And then the modeling assumptions that he has here: what is the dimensions for the connecting rod, and what kind of solid model that you have here for the connecting rod, and then you can put it inside of a box, a green box or a sandbox, and then he was able to use SolidWorks and import from SolidWorks into COMSOL. But if you cannot do that, you can just use directly COMSOL to produce the final shape or the geometry. And you have material properties that I mentioned to you. You have those will be input to COMSOL, and then you have now the ability to model this and mesh it in 3D. So finite element, you have meshing, and then you get some results for the solution to the cooling problem, because you basically have the connecting rod, and the connecting rod is cooling, and these are the temperature profiles as it is cooling, and he described that in greater detail by taking specific information. And now it'd be nice if you can get information on the grain size and distribution of grain sizes and what have you. So this is all open process design optimization. It's up to you how you do it. And there are some information that you can look at material science book on the what you call the TTT diagram, time temperature diagrams, for the formation martensite, pearlite. These are different phases that come out of steel, and that can enrich actually your discussion of the connecting rod. So these are here discussion and results, and then conclusions, and then you can have some additional material for appendices and so forth. So this is one example of the connecting rod. I can bring up another example, which is a different type of report, as you can see here, by Brad Witkowski, was a student of mine in the past, and he did also a very good job in modeling in particular, because he wanted to, like, similar to what I talked about. But you can see here, this is the, for example, the discussion of the casting and the formation of martensite and so forth is pretty detailed. And then the discussion on the modeling and the modeling assumptions. And here you can go into all of the continuum equations of fluid flow and heat transfer, as we will learn in the next lectures and so forth. And then you can do some heat transfer modeling, and you can model the transition from the liquid to the solid with some not really abrupt way, but a smooth function that goes from the liquid to the solid, and that can allow you to do the modeling in COMSOL. Also, we will learn something called the Stefan problem, and the Stefan problem is the classic problem that people solve to study solidification. So he did discuss the Stefan problem, and compare the analytical results to some of his computations in finite element. And with this, I think you have a very good idea about how to start your project and how to continue with that. I might add that I may be able to tell you a little bit about how to access the SEAS account if you stay with me just for a little bit. So here, if I go to finding I'm going to try to find a file that has information on the accessibility to the SEAS account, and I think I have this in one of the online lectures or the lectures here for another class. So if I have maybe the first lecture, introduction, then it might have this information. So let me see if I can do that to find the information on the accessibility, although it's from a different class, but I think the information will be useful for us here. So here. So if you look at here, you can create a SEAS account. If you do not have a SEAS account, you go to this site, and then it requires 1 business day to process. And then once you have a SEAS account, then you can remotely connect to the server, and the server's name is remote.seas.ucla.edu. And that you can, once you have their remote, then you say connect, and it will authenticate your account, and you can start either MATLAB or COMSOL or Abacus once you're over there. If you are not familiar with the remote login process, I'm going to try to see if I can do that to show you in here. I guess it is in the utilities on the Mac, and the utilities, let me see again, utilities, and the utilities, I have it here. Maybe it is, yeah. Well, I'm not sure. So I think you can find it on your remote desktop, and you'll be able to log on very easily to the remote seas.ucla.edu, connect, and then it will turn your system into a computer as if you are actually sitting on your PC, and then the COMSOL or MATLAB or SolidWorks will be available to you, and you should be able to try them very soon. So I think I'm going to stop here, and that would finish our discussion on the project and comments on how to access the data.